مرحبا، أنا أحمد القضاء and this is my partner ماريو القلاب. unfortunately حلا بركات اليوم ما قدرت تيجي، عندها ظرف معين ما قدرت تيجي مشانه، فهي راح تصور كيف طريقة الحل وتشرح عنها. So basically احنا عندنا هذا البيم of rigid body، عندنا هاي الطابة الصفراء اللي هي الرولر، وعندنا هذا اللي هون اللي هو الفيكست سبورت. وعندنا هاي السوفينير عشان نقيس فيها الفورس. طيب تمام. هسا احنا زي ما عرفنا بالستاتكس عندنا الرولر انه بس بيعطي انه هاي عندنا هاي البوينت A وهاي البوينت B. سو بوينت A عندنا اياها انه هي راح تعطي AZ، والبوينت B راح تعطينا اللي هو BZ و BY ومومنت اون B، عشان انه هذا الفيكس سبورت زي هيك. الديستانسز تبعون البيم عندنا هون هاي 30 سنتيمتر، وعندنا هون النص اللي هو 15. لما نحط اللي هو السوفينير هاي هون ناخذ اللي هي بنص ال 15 اللي هي 7 ونص. وهلا ماي بارتنر ماريو راح يشرح لنا كيف احنا بنطلع الفورس لما يكون عندنا ويت معين. هلا عندنا انه هون عندنا طريقتين راح نستخدمهم، اللي هو في طريقة الميزان والكالكوليتر، وعندنا هاي الطريقة اللي هي تبعت الفورس ميتر.
تمام. هلا we want to apologize briefly على السيتنج اللي احنا فيه، بس للاسف ما قدرنا نشتغل في الورك شوب اللي عندنا في الجامعه. وواحدة من الريجوليشنز تبعت this particular project كان انه ممنوع نستخدم ال privileges اللي عندنا اياها as university students. ف we compromised and we made do with what we have. طبعا كل الايتمز اللي شايفينها قدامكم نقدر نلاقيها في البيت، من طابة ل wooden plank ل tape ل scale calculator and so on and so forth. تمام. فاحنا زي ما بنعرف انه الفورس تبعتنا لازم تكون الماس باليونت تبعت الكيلوغرام. احنا عندنا هون السكيل تبعنا بعطينا however بالجرام، فرح احط انا simply الايتم تبعي على الميزان، رح اكبس الباور بutton ورح يطلع عندي الريدنج. بالنسبة ل this particular item عندي 129 جرام، بحوله لكيلوغرام using a simple calculator، بضربه ب 1000 عشان يعطيني كيلوغرام. بعديها بضرب الكيلوغرام ماس بالجرافيتيشنال فورس اللي عنا اياها احنا على Earth on planet Earth. طبعا في الكورس موجودة عندنا 9.81، بس في كمان كورسز ثانية بتستخدم 10. عشان نعمل calibration على graphical plot عندنا، طبعا رح يكون weight مع distance. اللي رح اعمله هو رح استخدم كرافتي او نحكي DIY فورس ميتر. رح احط simply عندي انا الاقلام، عندي مسطره، رح احط simply الايتم تبعي هون و it's going to pull down. طبعا الديستنس اللي رح تنزل عندي، تمام، هاي الديستنس we will relate it to the weight اللي عندنا. فلما نطلع احنا الجراف تبعتنا بالاكسل او any other software رح نستخدمه، رح يبين عندي ال relationship as a straight line، و based on that رح اشوف انا مثلا different items how they behave. بالنسبة ل this experiment رح نستخدم only this item، رح نحطه على distance 7.5 زي ما حكى احمد، ورح نقيس الفورسز اللي عندنا والمومنتس.
So, in physics and engineering, a free body diagram is a graphical illustration used to visualize the applied forces, moments, and resulting reactions on a body in a given conditions to calculate reactions in a mechanical problem. Now, the body may consist of multiple internal members or be a compact body such as a beam. A series of free bodies and other diagrams may be necessary to solve more complex problems. These diagrams are frequently used both to determine the loading of an individual structural components and to calculate the internal forces within a structure. They are mostly used by engineering disciplines from biometrics to structural engineering. Now, a free body diagram is not a scale drawing, it is a diagram, and the symbols used in a free body diagram depends upon how a body is modeled. free body diagrams mainly consist of a simplified version of the body, which is often a box, as in here in the example. Forces shown as straight arrows pointing in the direction they act on the body. Moments are shown as curves with an arrowhead or a vector with two arrowheads pointing in the direction they act on the body. And we also have one or more reference coordinate systems, which is the X, Y, and Z. In our example here, it's only going to be a 2D body diagram, so it's only going to be the X and Y. Now, the number of forces and moments shown depend upon the specific problem and the assumptions made. Common assumptions are neglecting air resistance and friction, and assuming the rigid body is in action. Now, in statics, all forces and moments must balance to zero. The physical interpretation is that if they do not, the body is accelerating, and the principles of statics do not apply. However, in dynamics, the resultant forces and moments can be non-zero. Now let's talk about our idealized model solution. Here we have the reactions at A and B. We replace them by forces at A and B. Now the force at A must be vertical because its roller support can only react perpendicular to the surface upon which it rests. Now the line of the 1.26540 Newton load and the reaction at A have no horizontal components. So it should be clear that the horizontal components of A must be zero. Therefore, we assumed a horizontal component at A and showed it on the free body diagram. We would find through the sum of the horizontal forces equals zero. Everything that is needed to solve the free body diagram is shown. Now we use the free body diagram and the principles of equilibrium, which is sum of forces must equal zero, and sum of moments also must equal to zero, to solve for the unknown forces. If we try to solve for the moment forces, which is the MB in this case, we would have two unknowns. Therefore, we are going to use the equation, which is the summation of Fy equals 0, to end with one unknown for the original equation of MB. Now, if we take the moments around point B, sum of MB equals 0, so we know that the absolute value of the counterclockwise moments must equal the absolute value of the clockwise moment. Newton's third law. The couple moment interactions between a free body and its surroundings obey Newton's third law of motion. Now, the law states that if a body exerts a force or a couple moment on a second body, which is considered the surroundings, then the second body exerts a force or a couple moment with the same magnitude but opposite directions on the first body. Here we're going to talk more about the external and internal forces. Now, the forces external to a free body exerted by its surroundings are referred to as external forces. The external forces can act on the outline, which is the outer surface, or the internal points of a body. For example, the effects of gravitational, electrical, or magnetic fields exerted on the external forces at internal points of the body. A graphical demonstration of a free body subjected to external forces is the free body diagram. In addition to the external forces on a free body, there are also internal forces within the free body. The internal forces are forces between the particles of a body. These forces do not appear or affect a free body diagram, as they are inside the body itself and not externally exerted by the surroundings.